So, first of all, I will talk about the introduction. Inorganic chemistry serves as the fundamental basis for material science, providing the essential substances required to build and sustain modern infrastructure. The technical significance of construction materials is directly detected by their internal structure, the arrangement of atoms, ions, and molecules, and the nature of their chemical bonds. In this presentation, we will explore how metallic bonds allow for the high ductility and strength found in the structure. For example, steels and cement, which are vital for supporting heavy mechanical loads in body. By understanding the classification of this material from simple elements to complex composites, we can better appreciate how inorganic chemistry ensures the reliability and longevity of the structure around us.
For this presentation, our main objectives are to explain the role of inorganic compounds in modern construction and why they are essential in building structures today. We will also describe the chemical properties of these materials that make them strong, durable, and suitable for construction use. In addition, we aim to identify innovative inorganic materials and technologies that currently apply in the construction industry. Lastly, this presentation will highlight the industrial application of inorganic compounds and discuss their sustainability impact in supporting safer and more environmentally friendly construction practice. Let's move on to the importance of inorganic compounds in the construction industry. Inorganic compounds are generally compounds that do not contain carbon-hydrogen bonds and are commonly derived from mineral and metallic sources. They serve as the main components in essential construction materials such as cement, glass, and steel. These compounds are important because they provide high mechanical strength, excellent thermal stability, and strong chemical durability. Due to these properties, inorganic compounds contribute to safety, strength, and long-term durability of floating and infrastructure.
Hello, I'm Norimanda Kira and I will talk about the chemical properties behind material performance. So first, I will talk about the chemical properties for cement and concrete. Cement and concrete get their strength from hydration reactions. When cement reacts with water, compounds like tricalcium silicate and dicalcium silicate form calcium silicate hydrate, which is the main source of strength. The material is highly alkaline with a pH around 12 to 13, which helps protect steel bars inside concrete from rusting. However, concrete is chemically weak against acid, which can react with calcium hydroxide and reduce durability. Secondly, glass. Glass is mainly made of silicon dioxide, forming a strong covalent network structure. Unlike crystal, glass is amorphous, meaning its atoms are not arranged in a regular pattern. The strong silicon-oxygen bonds make glass chemically stable and resistant to most chemicals. However, glass can be attacked by hydrofluoric acid, which breaks the CO bonds. Its chemical structure also gives glass good thermal resistance. And lastly, steel. Steel is an alloy of iron and carbon, where metallic bonding allows atoms to slide without breaking bonds, giving steel its toughness. Carbon atoms feed into the iron lattice, increasing strength and hardness. Steel can undergo oxidation, producing rust when exposed to water and oxygen. In stainless steel, chromium reacts with oxygen to form a thin chromium oxide layer, which prevents further corrosion and improve performance. In conclusion, the chemical composition and bonding of cement, glass, and steel directly control their strength, durability, and resistance, making them suitable for different engineering applications.
So the next part is innovative and sustainable inorganic materials. The first material is cement and concrete innovations. So the innovation is low carbon cements and geopolymers. Limestone calcined clay cement, a low carbon alternative that replaces part of Portland cement with calcined clay and limestone, cutting CO2 emissions by 30% compared to ordinary cement. Geopolymer concrete use industrial byproducts like fly ash and ground granulate, blast furnace slag to create inorganic aluminosilicate binders instead of conventional cement. Significantly lowers carbon footprint and boosts durability. The next material is glass innovations. The first one is recycled and low energy glass. Recycled glass in building materials. Using post-consumer glass as aggregate or insulating material cuts energy needed for manufacturing by 30% and reduce the need for virgin raw silica. The next one is lower temperature glass processing. Oxyfluoride glasses. By incorporating oxyfluoride glasses into end-of-life photovoltaic glass, researchers can lower melting temperatures, reducing energy input and enabling reintegration into new inorganic glass products. Then the last one is functional glass technologies. Thermochromic and electrochromic glass. Material whose optical properties change with temperature or applied voltage to regulate solar heat gain. Inorganic coatings or doped glass systems. Emerging search area. The last one is steel and metallurgical sustainability. First one is recycled and circular steel. Recycled structural steel. Steel is 100% recyclable without quality loss, making it inherently more sustainable than many virgin materials when system capture and reuse scrap. The second one is decarbonization technologies. The first point is pyrocycle carbon recycling. A tech that recycles CO2 within existing blast furnace basic oxygen furnace systems, reducing emissions without full plant rebate. The second one is hydrogen-based steelmaking and Hisarna processes. Emerging approaches to replace coal with green hydrogen or to streamline iron production for lower energy use and emissions during steel making.
So next, for discussion, firstly, we have cement or concrete. Cement is mainly made of inorganic calcium silicates and calcium aluminates, which are core compounds studied in chemistry 361, solid state, and coordination chemistry. When water is added, a hydration reaction occurs, forming calcium silicate hydrate. This inorganic gel creates a strong binding matrix which gives concrete its high compressive strength. In reconstruction, this reaction allows concrete to harden inside building foundation, bridge, and roots. Studies shows that the chemical composition directly controls durability and learning behavior, affecting long-term safety of structures. Next, for glass. Glass is mainly composed of silicon dioxide and inorganic network solids discussed in chemistry 361, bonding and lattice structures. Strong CO covalent bonds creates a rigid but transparent structure. Because it is chemically inert, glass does not react easily with water or air. This makes it suitable for windows, building, facades, and solar panels. Tempered and laminated glass improve safety by controlling fracture behavior, which depend on inorganic bonding strength. So next, we have steel. Steel is an inorganic alloy made of iron with carbon and alloying elements such as chromium and nickel. In chemistry 361, this relates to metallic bonding and crystal lattice modification. Steel has high tensile strength, so it is used in reinforced concrete and skyscrapers. Corrosion occurs when iron reacts with oxygen and water, forming iron oxides. Galvanization, which is zinc coating, protects steel by sacrificial oxidation, and electrochemical concept from inorganic chemistry.
As for conclusion, inorganic compounds are essential in modern construction due to their strength, durability, and chemical stability. Their properties such as resistance to heat, corrosion, and mechanical stress make them suitable for building strong and reliable structures. Advances in innovative inorganic materials have enhanced construction performance while supporting sustainable practices. Overall, the use of inorganic compounds contribute to efficient industrial applications and promotes sustainability in the construction industry.